Okay, so what we are going to do today is basically the heart of condensed matter physics. We'll write down in second quantization the Hamiltonian of interacting electrons on a lattice and see what kind of physics comes out under different assumptions, approximations. And basically, once we'll finish it, we'll move over to Dirac equation. Just till now, everything that we did is non-relativistic, and it would be a real shame here finishing advanced quantum mechanics without knowing something about how relativistic quantum mechanics works. And then basically I intend to do something about path integrals, and to finish I'm still debating with myself to go back to quantization of an electromagnetic field or do perturbation theory and Feynman diagrams. I don't think we'll have enough time to do both. Actually, how many people here are really interested in electromagnetism optics?
No.
How many people are doing it without to be interested in it? Okay, okay, so we'll see. Okay, so where were we last time? Basically, we did the non-interacting part. We came out with and we also added that T and M shouldn't be too far because the overlap between wave functions that are centered around the M position in the lattice and the N point in the lattice falls off exponentially, and in a moment we'll actually be more specific and say that it's only for nearest neighbors. Okay, another assumption that I did here is I assume that we have a single band. Usually for the same reasons, if I have two wave functions that are far energetically one from the other, their overlap is also quite small. Okay, so what do we do about the interaction? Well, we have the recipe. We did it actually 2 lectures ago. We have 4 creation and annihilation operators. Therefore, we have points M, N, R, and S. Sorry for using the same S. and two possible spin directions, sigma and sigma prime. And this matrix element, I write down here. It's the usual Coulomb interaction term. Or I can now write a general term here, adding an additional term here. Okay. I'm still very formal. I didn't say much about the physical content.
What does it mean that they are not interacting?
No. Once I added this guy,
Okay.
I changed it into interacting. If I'm looking only on this term, this is non-interactive. Okay. So let's start by solving the non-interacting case.
The term that's circled in red is the same term.
It's
the
this
second-
term. Yes, I just changed notation because you'll see in textbooks and otherwise either this notation or usually this notation. But as you will see in most physical examples, I won't use even for this form. I'll try to simplify it.
Okay.
And even in the simplified version, it's not always trivial to solve. Now we'll do something that is almost trivial, and that's the solution of the of the non-interacting case. Okay, so an additional simplification. Okay, the simplest assumptions that I can do. If n and m are equal, so I have some it's called on-site energy. Okay. A lot of times people just give it a 0, but it doesn't complicate life, so I'll leave it in the meantime. This is known as hopping, or nearest neighbor hopping, if you want to be more exact. Why? Because I'm annihilating the particle on n and creating it one to the left or one to the right. If I have a 2 or 3 dimensional lattice, it will be the nearest neighbors according to the structure of the lattice. And all other terms, I'll use the argument that it's exponentially small and assume it's equal to 0. Sometimes for certain lattice structures, one of the most famous of them is carbon nanotubes or graphene structures. It's important to take not only nearest neighbors, but next nearest neighbors. You can envision that the distances between nearest neighbor and next nearest neighbor is not so different. But in 1D, no problem at all. Okay, so let's write down the non-interacting Hamiltonian. I'll call it H0. Now you can see very easily why I call it on-site energy, because if there is an electron, I pay energy epsilon to sit on this site. Okay, and here is the hopping term, which tells me I can move one to the left or one to the right. Why is there a minus there? Someone knows?
Because they gain energy.
Exactly. As if I would have here a positive term, it will mean that the solution is very easy. Don't move, stay on the same site, which is solution, but doesn't correspond to the physical situation, where to squeeze a wave function to one point costs you a lot of energy. And you know that if you're just leaving a particle and even starting, even not on a lattice, just in a box or a free space, starting from some initial wave function that is very localized in space, it will spread out. So this is just this term. What I have to have here a term that is hopping to the left and hopping to the right. First of all, on physical grounds, there shouldn't be any difference from hopping from left to right to hopping right to left. But also on mathematical grounds, if I have only one term, this Hamiltonian is not Hermitian conjugate. You operate a dagger on it and you'll get something else, which cannot be. Okay, so this is what I have to solve. How would I solve it? From your knowledge of physics?
Fourier.
Fourier, right. What else can it be? Basically, it's the same like a free particle. If you remember anything out from your third year condensed matter or solid state course, the only difference is that K would be quantized. That's it. Okay, so let's use the games that we have already used here. Basically, take the description of creation and annihilation operators in K space. The usual Fourier transform. Anyone remembers why it's between pi over a and minus pi over a?
The Brillouin zone edges.
Exactly, that's the Brillouin zone of one-dimensional lattice. And now a bit of simple work of replacing each one of the C's here with its Fourier transform and seeing what we get out of it. I'm doing it because first you have to see it once, and second, the result is cute in its simplicity. So let's look on the first term. Okay. Here simply all dependencies on n falls off just because you're taking the complex conjugate of what's appearing here. You lose the phase, you lose everything. So I'm not using even sigma here for simplicity. Okay, the more interesting case is the hopping term. Minus. Well, here I'll be a bit more careful in putting sigma. No point. Just nothing more than installing this definition into the hopping tool. Okay. Now I'm looking at this. Remember, I have an integral on n. Okay, so I'll take out everything that doesn't depend directly on n here, and then perform the summation on n. Any other primes missing? This is just Kroneker's delta. And I can replace this by twice plus 7. And I'm finished.
So we do
Because instead of this term, I can just write term is diagonal. So you just count how many particles you have in each case state, which we are doing fermions. So either 0 and 1, and sum up. Okay, did you see the usual type binding solution to this matter? That's exactly that. Okay, so we really didn't have to apply this heavy artillery to solve this problem, but at least we got the correct answer. Good. What can we see on? What can we say about the interaction term? Are all terms here equally important? And the easiest is to look on this integral. From where will come the largest contribution to this term?
the closed one.
Excuse me?
The closed in space.
Even better. All are in the same space at the same point. So let's look what happens. All of them are at the same point. I have just summation over n, the point. In a moment, we'll drop this ridiculous notation. Okay, this is a term. By the way, what would change in the previous solution if I took sigma into account? Basically, only an additional summation on sigma. Since the hopping doesn't flip the spin, if I started with a spin up, I'll end up with a spin down, or the other way around. So all I have to add here is an additional summation on sigma. Could there be physics where there are spin flips? Yes, but then you have to put in the correct interaction. Here we assume that just simple hopping, that's all we have here.
So you're taking into account only the case.
Only Coulomb interactions between the electrons, no magnetic interaction. It's not such a bad assumption, because usually the direct Coulomb interaction is much stronger than anything else. There are, though, types of lattices, especially if there's if the atoms themselves have a permanent magnetic moment where it can play a role. But here we didn't assume anything. Okay. Let's distinguish between two cases here. If spin is in the same direction, what will happen?
They have different momentum.
It will be zero.
It will be zero.
Has to be zero. Two electrons with the same spin can't sit in the same state.
Only if they have the same momentum.
But I'm writing down this term in n space, in position space. I'm still working with this definition. Before, I didn't use yet the Fourier transform here. Okay? So, it's equal 0. This is known as Hubbard interaction. Defined as, instead of writing down 2 times u n n n n, we're just writing 1 u. Why is there 2? Because one could be sigma up and the other down, and vice versa. So I have 2 different ways to do it. This term actually is extremely important in understanding why certain metals have, or certain atoms even have a magnetic moment. Why? Let's assume I have an atom with several energy levels. Okay. If I'm taking into account only the Hubbard interaction, okay, and let's say I want to put into it let's start with 2 electrons. Okay, so let's put one up. Where would I put the one with the down? Okay, that's a minimal energy. It's a minimal energy if I don't take into account interactions. Because this state is actually the state that the Hubbard is the strongest. Because they both, physically, both occupy the same wave function. Therefore, it's maximum interactions. Because whenever one has a high density, the other one has high density. So, it might make sense to move the other electron, the other spin direction, to a higher level, and depending on the difference here, you might gain energy. And if you gain energy from such a thing, actually, to make sure that it won't be in this situation, I flipped it up. So here, this situation, let me use a different color. This has total spin 0. This has total spin 1.
Just moved it up to.
Which situation is better? Well, the answer is depends. If this level spacing is large, it's better to sit in this situation and pay a lot of energy on the interaction, because you'll pay even more if you'll move it to the next level. On the other hand, if the level separation here is small, level spacing is small, makes sense to pay a bit kinetic energy and to pay a lot less interaction energy.
Why do you flip it?
Because then you actually make sure that you'll never go back to the lower state.
But
Or if you want, you can put either up or down with the same probability, but still you will have a lot of atoms with 2 spins in the same direction.
But if it was excited, then why would it go back? You would pay energy to go back.
Okay, but this way you actually make sure that it never can go back. You have virtual processes. I don't want to get into the whole details, but that basically that tells you that atoms which are almost degenerate at the last fill state have a tendency to have a magnetic moment. Atoms that have a large distance to the next state won't be magnetic. And this is actually in chemistry, also in physics, is also known as Hund's rule. Okay, the Hubbard model is like the bread and butter of interacting systems. As ridiculously simple as it looks, it's not solvable analytically. Even not in it makes life very complicated. In 1D you can still do something with it. On lattices larger than 1D, it's a pain in the neck to solve these things. So even the simplest, if you look here, we took the interaction term and simplified it almost to bare bone. Nothing is left almost, and even that is not simple to. Well, it's if you're talking about the equal or larger than 2, you have no closed analytic solution for it. In 1D, using the more or less the things that we have seen in the previous lecture about linearizing around the Fermi energy and everything else, you can make almost analytic solutions. But larger than 1D, no, nothing. Okay, so you would say, what's the point on looking on more complicated terms? The reason is that I want to look here on an additional term for the reason that provides you with a physical mechanism which can create long-range magnetic behavior. Okay, so we'll go and do this. Okay, so the next case I'm looking at is equal to S and N. Why is that the next contribution? Look what's happening here. On the same x prime, n is equal to r, and n is equal to s, meaning I have their psi square, so it gives a larger contribution than just picking 4 indexes at random. Okay. So now I have a summation on two indexes. Okay, just this is n point n, these have to I've contracted these, and they have n on point m. And basically you can write it down simply as the same for here. Okay, and this term is known as the direct term. This is basically what you would have expected just simply from contemplating what is a Coulomb interaction, right? The charge here, the charge there, this terms that depends on the falls off like 1 over the distance between them. Simple Coulomb case. Turns out that we have another case that is important and mainly important for the magnetic interaction. Here we have no magnetic interaction, it doesn't matter. All you do is sum up the total charge at one point, at another point, calculate the Coulomb interaction between them, sum up on all the points in the lattice, go home happily. Yeah.
But you're missing the Coulomb interaction between inside the same state.
That's a Hubbard.
Okay.
It's there. That if you are taking only one element, take the Hubbard term. Now I'm looking on additions. So Hubbard is point on point. This is two different points, but still it's a contribution. And the reason that you can't, well, you should stop and think about it, because indeed Hubbard is much stronger, but here you have a lot of different possible points and all of them can contribute, and they usually, unless you have some screening or some reasons that the interaction falls off quickly, a lot of these points contribute. I'm still looking only on 2 points, but now exchange their positions between the different signals. One is so writing it down explicitly. So very pictorially, what happened here? If I started with 2 spins on M and N like this, after operating with this operator, I end up with the other way around.
But the sigma prime is not necessarily, doesn't equal sigma. So
No. Look what's happening here. In a moment I'll define it exactly. There's an interaction that if the 2 spins are in the same direction you lose energy. If they're antiferromagnetic, they gain energy. So, assuming that you believe what I have written here, and in a moment we'll go into the details, but I want first to see the physics of it. This term basically tells me that if I take only Coulomb interactions, what will be the magnetic state? If I lose energy for being parallel and gain energy for being antiparallel, what will be the ground state?
Zero.
Ferromagnetic. Basically, all the metals that exhibit magnetic properties, the best known iron, that's the reason. They gain energy by having the spins of the electrons in the same direction. So it's a mechanism that has nothing to do with the atoms, it has to do with the electrons. It's also known as itinerant ferromagnetism, ferromagnetism that comes out of the electrons. Okay, now I have to first clarify what is this term, what is this operator, we didn't define it. And at least sketch how to get it. Okay, so should define what this term is. And as a refresher, these electrons are spin half entities. Okay, so let's look for a moment. Okay. All what you have learned about spins last year in 2 minutes. Maybe 5 minutes. Okay, this should look familiar to you. Okay? A general state of spin, alpha, with some linear combination. Okay. If I'm given a state alpha and I want to know what is the magnetic moment in a direction x, y, z, or 1, 2, 3, there are different notations. I wrote both of them. You use the operator, which is the Pauli matrices for each direction, x or y or z, and you get the expectation value of the spin at some direction. Okay? Questions still here? Yeah.
Comment. In sigma 2, the I in the second row is positive.
One of them has to be positive, and indeed in the second. Okay, so that we know. So what's the meaning of this guy here? As usual for a 2 operator in second quantization. What do I have here? I have alpha and alpha prime, which in the case is that I have 2 different wave functions here. And vector because I have x, y, z. Okay, I'll write down one term explicitly, and this is this term. Quarter I have all the way through because I have 0.5 in the definition. Okay. So at this point, at this time, you either lost me completely or are bored out of your minds. But the point is, and I won't do the end of it here, but take this definition, check at home if you understand why it's defined this way. If not,
You use the Pauli matrix and you.
yeah, I just wrote the three terms of the Pauli matrix. Except for this late hour, there's nothing clever here. It's just a lot of indexes. That's all. But you take this definition, put it in here. This, you know what's the definition we defined previously. Check that you return.
And then you find the J.
And then you find the J as a combination of U, M, and the important thing is actually, the interesting physical knowledge gained from it, and that's the most important thing, you ended up with an interaction between the spins, where in the original term, it wasn't clear from where you have it. And this term is known as the exchange term. Yeah.
How did we get from this expression of U M N M N to J F M N?
If I'll give you a secret. That's it is just UMNMN. You're not convinced? Finish up the calculation and see what you have here.
The exchange term is J. You mean in J? It's J.
Look, usually you push this thing into a renormalization of the U, what was it called, NNM, because this term is the same, so basically instead you have your minus a quarter, instead of having here this guy as equal 1, now it's 3/4. Important if you want to calculate a specific value, not very important in the meaning that it doesn't have a different structure to this interaction. It just corrects the prefactors. This is already interesting because it gives you some physical behaviors that you weren't aware of it previously.
So the Coulomb interaction creates an interaction between the spins?
Right. Coulomb interaction and basically the fact that you can in quantum mechanics move the spins on two of and they are the same. Or if you want, it's a combination of having fermions that can't be in the same state. I'll give you a very transparent and simple explanation why you can get magnetic behavior out of these terms. And for that, you need only two sides. Let's assume this basically is a cartoon version of all exchange. Two sides. Two electrons on two sides. Okay, now you can ask me, will it be better to be in this state or in this state? Okay, so basically you would look at it and say, who cares? This is sitting here and this is sitting here, and they don't speak with each other. I didn't put in explicitly a magnetic interaction, right? But let's stop for a moment and look a bit more closely. Basically, if both of them are up, spin up or vice versa, spin down, doesn't matter, that's the only component of the wave function that can come into the game. Why? Because I can't have a situation where this moves here. I can't have a situation where this moves here. So basically the energy of this state is extremely simple to calculate, just 2E. I finished, I solved the problem. Okay, I'm looking on this problem. Well, of course I have 2 electrons, it's still 2E. But here I can have already a whole bunch of states. Why? Because four, 2 is enough, and okay, these in principle could exist. So if I'm writing a linear combination of these guys, why is it good to add components of this wave function into the solution? Because that will add you minus 2t, because they can hop from each other. On the other hand, it's higher energy. The Hubbard energy is higher. Same here. Meaning that if I go and measure the wave function on different positions, I can have here a magnetic interaction, right? Could be worthwhile to create a situation like this instead of like this, or vice versa, depending on exactly the interaction terms. So I didn't put here anything with spin interaction, and nevertheless I can have here the orientation of the spin can play a role. And if you think about it, at the end of the day, it's the Fermi law. If I can move, at least in principle, into the next state, or I can't. And that depends on the orientation of the spin. If U is very big, I never want to do it. And it's ferromagnetic. If U is small relative to T, happily I'll do it. I'll pay the price of interaction when I'm sitting on each other and gain a lot of kinetic energy. So it depends on the parameters of the system. So that's like the simplest toy model that one can draw a cartoon why, although I didn't write directly an interaction between spins, they are important in the interplay between Coulomb and kinetic energy plays a role in determining what will be the orientation of the spins, of the magnetic moment. Okay. Have you seen Bogolubov-Dejean transformation? I think you should have seen.
Yeah, in the last tutorial.
Okay, so
That doesn't mean we understand it.
no, why am I asking? It's again like with this game. I can write down a whole bunch of 2x2 matrices and diagonalize that and go into the details, which will take a long time, or I can concentrate on the physics. So if you have seen it, I know that I can do actually the second, and whoever wants to see the details, just repeat or go in any of the textbooks it shows. Okay, so basically we got here the simple Coulomb interaction. There is an additional two phenomena in condensed matter where you have interactions that are, I would call it, counterintuitive. Meaning that we get their interactions between particles, that although we have a Coulomb interaction which is repulsive, at certain states we get a a net positive attraction between them. Now, how do you get it? At some level, it's understood, well understood. That's the BCS theory, which assumes that you have somehow interactions between the electrons and the phonons turn a net interaction which is positive between them, creates pairing, and we get superconductivity. And we have the new superconductors, which is a bit less established, but nowadays at least it's going toward conclusions that it has some, or at least part of these systems, has something to do with antiferromagnetic interactions that exist in the lattice that also mediate positive attraction between the two particles. What we will do here in the next lecture is assume that we have positive attraction between the electrons and see how you get out of it superconductivity and what does it mean physically. If you want, in a 2-second highlight, if you have a positive interaction between the electrons, you basically can look on the two electrons as a bound particle or a bound state. And if we have two spin-half particles, which are fermions, the bound state becomes a boson. What do we know about bosons? They can occupy the same state. So that is basically the physics behind superconductivity and also superfluidity. But what we'll do next in the next lecture is, as I said, assume that the nitty-gritty part of Dejean-Bogolubov transformation you in principle know, so we'll start from the physics, write down what we have to write down. I'll tell you, okay, we will perform a Dejean-Bogolubov, and this is the result that we get. The end, and what is the physics behind it. If we'll be lucky, towards the end of the lecture, we'll move on to Dirac equation. Okay.
Thank you.
Thank you.
Thank you.